Big focus of becoming what they're going to do there. Hello. Nice to meet Yeah, but what is so in the fabric? But yeah, it took me about so much conceptual just to make it.
Yes. I mean, there's
Why? Also, is in the list.
something to take over. We didn't
Should I put there?
I guess.
The list of contests exactly so far it sounds like they just some solvents.
Or you can add, but they
Linnea sees to. Now we can start. Yeah.
Hi, welcome. Welcome again, those who have been with us before in the day. And welcome for the first time those who are coming now. I'm Daniela Mendoza, assistant to the Challenge Lab, and this is Saeed. Saeed is a student to the Challenge Lab, but he also has a talent that he's going to show to us. A fun fact, Saeed is going to present it. And just before he starts, I want to remind that in the challengelab.org, we have all the abstracts of all the presentations that have been running so far. So if you're curious about another presentation, then you can just access it there in publications. Okay.
Yeah, so I want to say that the song that you're going to hear, I just made it during the challenge lab. So it's kind of fun presentation of my feelings. Yeah.
Thank you very much, Shai. And now I would like to present Linnea. Oh, sorry. Yeah. I would like to present the students that are gonna give a bit of an introduction about the Challenge Lab. So part of their thesis was phase 1, what we call the Challenge Lab process, and part was about doing their specific project. So right now we're gonna talk a little bit, or the students are gonna talk to you a little bit about what they did in their phase 1, so the Challenge Lab process.
Not a good day.
Reverse engineering. I was. Okay, so welcome. It's nice to see so many people here, and great to see that you're here to listen to me. And so, as we said, we're going to shortly present you how we've been working here in the lab for the past few months, going through the sort of background of the data here, showing you some of the methodologies and the tools that we have been using with an emphasis on the associated phase 1, and you will understand more what that is about very soon. So first of all, we have the team. We have Eduardo, the top left corner from Spain, Amalil from France, Konstantin from Lithuania, Tanya, Eric, and me, and Linnea from Sweden. And we have Guillermo from Mexico. We have Cuarán and Andres from Colombia. And then we have Panuak from Thailand. We have Said from the violin, from Iran. And then we have Saravana from India. So that's the team. So we have 8 nationalities representing 7 different master's programs here at campus. So that's us. And the idea here is actually we are here in the middle of this. So what is this? Yes, we have this is the so-called triple helix, where we have the private sector representing the green circle, the public sector representing the blue circle, and we have the academia. And here at the lab, we are change agents. So we are not standing behind the public sector trying to do the system, and we are not standing behind the private sector, and we are not, I can't jump that high, but we are not behind the academia, we are actually here in the middle, meaning that we are in some way neutral towards this. That is the idea of the change agent. We're not representing anyone but ourselves as students. And as John mentioned in the beginning of this day, it is quite good to represent a student because you're not really threatening to anyone. Everyone knows what a student is, and everyone can relate to the situation as a student. And we don't have any hidden agenda to fool someone and take some kind of decision, or at least I don't. And the main methodology we'll be using here is the backcasting methodology, where we actually, when we met here in the beginning, we did not look very much at today's situation and think what is wrong today, what is it we want to change. But we actually stepped out of that for a while and discussed what is it that we really want in the future. How do we want the system to work, and how would we like the work to be? So we kind of defined some general criteria on that, and then we analyze the current situation in relation to these criteria, check to see are there any solutions that fulfill the criteria we have, and lastly, how can we get from today to the desired future. And that is what we will describe now, and I think it's your turn, Simon.
Okay. So we have the backcasting and the basic methodology in the challenge, but we have two perspectives as well, outside in and inside out. In the first week when we started the challenge lab, because we believe that the students in the challenge lab are change agents. So in order to be a change agent, you should know your values and your strengths. So in the first week of the challenge lab, we had a workshop to understand inside yourself, what is the thing that you can burn for it, and what is your value very inside yourself. And so we had some practices, we had some surveys and some kind of games to mix it with fun. After that, we have some activities. We can see we have, for example, that active listen, to be able to listen to each other and share. So, because we worked together on 5 months, so it was really important to know each other. So we had some group activities. We mapped our strengths. For example, I said I'm good in socializing. I'm not good in analytical calculation and all this stuff. So we could see, we were standing in different places to see, okay, that person is really good in calculation or in a very detailed issue. So because we were going to make a group and work with each other, so it was very beneficial to see the values and influence of each other. And apart from this, we had some dialogue meetings, so we could, I can say those were like workshops that dialogue facilitation. He came and talked about how you should try to understand the people that you are going to interview, because we had a lot of interviews in our project. So he helped us to just don't look at from our perspective to the problem. So you should consider the other stakeholders and you should put yourself in their board as well. So by having this workshop, we were really lucky to have this chance to be able to first understand our values and our strengths, and after that try to communicate with each other during the whole
So this was the inside perspective, another one, which is outside in, as Johan presented before. Backcasting was the main methodology. And the first step of this methodology is defining the frame, which in this case it will be represented by the black line. So for that one, we also use a tool, which is the sustainability compass. Basically, the objective was to formulate a vision that we want for the future, but it's very difficult to come to a vision without that first establishing some criteria. And for that one, we use this way of visualizing and also categorizing the different criteria. And we discussed during those first weeks of the Challenge Lab, what do we want to be in that future. And the north, or N in this case, stands for nature. So the criteria here, well, we could summarize, we had 2 points. One, it was like less concentration of like artificial and human originated substances in the ecosphere. And also like resources and not over harvest what we have in the nature. The second one is economy in this case. And basically, we established that it's necessary to have a resilient economic system that doesn't collapse easily. And then also like having maintained what we have so far, so all the infrastructures and societal infrastructures that we have, maintained over time, instead of building new ones. Also like enabling further use of the resources that we already have in our systems. When it comes to society, we had another 2 criteria. Basically, one regarding the institutions in society, they should have these 3 these 3 concepts, which is transparency, also like accountability, and finally like mutual trust among them. And also like societal system should not be like an M, it should be like a mean, or like, sorry, like a tool that will enable, or a system that enable individuals to live together within the other criteria. And finally, the West stands for well-being. And basically here we look into the basic needs to be fulfilled for everyone. And also like we address the freedom of opinion, expression, assembly, conscience and choice. And finally, we had another criteria about social and economic inequalities are not justified. Actually here is not complete because this is unless this is for benefit of the disadvantaged members of society that will be the end of that criteria. And that was more or less what we had as a base for our vision, which is a sustainable future where we 10 million people in 2050 are able to meet our needs within planetary boundaries without compromising the ability of our future generations to meet their own needs. So that was more or less what we want. And now, Guillermo will explain the situation.
Yeah. Good. So, well then, the reason I wanted to explain you the second step of backcasting. So basically, from my perspective, it was my master thesis, because at this stage is when we actually get the insights, actually the perspectives of what's happening right now at a global scale, and then we're going further into the local, regional, municipal scale. Normally, as a master student, when you need to start your master thesis, you probably sometimes get a paper that says this is a problem. It's a brief description and that's it. And then all that you need to like think how to solve it. And that's quite vague. In the challenge lab, we had dedicated more than 1 month to basically look at the problem and be really to discuss at a global scale and how to approach it at a more local scale. That was crucial, I think, for most of the guys at the challenge lab to develop their master thesis. For this purpose, we used 2 tools. One is the funnel, which basically show how the resources are diminished and will be diminished in the the near future. And also you have increasing demands in terms of population, in terms of the economic. The economy has become more dynamic, so we should keep that pace that we already started. And understanding those issues also gets a little bit of curiosity on us as students to get into, okay, how can we act, how can we start doing something? For that purpose, and also within the Challenge Lab, we have the insights of actual projects that are happening now in Gothenburg, Sweden. One of them is the Lundberg District Factor 10, which is basically different are around the sustainable urban development, and you have different topics to approach from building environment, building technologies. You have also water management, and having the insight from researchers in Chalmers about these projects, we could get more information about, okay, that's an interesting project that I would like to work with or use as a case study in order to solve one problem at a more local scale. And this is, I think, the best part of the Challenge Lab. We got the opportunity to work with people from different backgrounds, but also from different countries. So, as a foreign student here in Sweden, it was really cool to get you to know which were the plans in Gothenburg for 2021, which are developed by the I realized that the government is working already in such issues at the mid and long term, and that was something that the Swedish guys helped us sometimes to translate stuff from those plans. So that was really cool, and yeah, that was like really good advice in order to continue our project. And I think now it's next phase.
So after we have done from inside out and outside in perspective, so now is the time that from broad to narrow down to our research topic. So in the last session, we have the session to have discussion with in the group. Challenge and what we have done so far to define what is the energies about what is our energies and what's the energy in the cities, what are they doing, and then we try to match between our energy in the system, right? And how can we define the research question and define the leverage point that we see that this is a good starting point that we can something and try to create change. So based on this session, we have this discussion with John, and we try to develop our research question. So this is what we have done in the Challenge Lab in the first phase.
Any questions about the Challenge Lab? Thank you, guys. Somebody has any questions about the Challenge Lab and the process? Then I would like to welcome Linnea and Andres. Linnea is from here, from Sweden, and Andres is from Colombia. They're going to talk to us about urban bioplanters for stormwater treatment of the mills. And as a fun fact, they came up with their own idea by being a pool in Chalmers. They were discussing about topics and ideas, and they came up with this idea. And as a comment, we really think that it's important for students themselves to actually come up with the ideas. So this is an important process.
Hello, everyone. As Daniel already presented us with that little kind of fun fact, we were swimming on a Chalmers swimming pool, and finally we came up with the idea after like 1 to 2 months dealing with this issue of motivation. So, this is forward. Yeah, so Challenge Lab and Chalmers University of Technology, as you can see in my shirt, really proud to present 2 students in this Cuarán. Thank you very much. And we are going to kind of, this is the program for today. It's kind of a glimpse of what we're going to present.
So we will start with an introduction of the problem. We want to tell you immediately our solution. Start with something.
Yes. Then we're going to explain to you what is a bioretention planter.
And we then explain the outcomes of our research and mining.
Then just a little highlight of what we did.
And finally, we want to.
Nice. So, what is happening right now in Gothenburg? It's, of course, a lot of things are happening.
And we do improved.
I don't know if you recognize this picture.
From the kids' picture, flooded. Flooding in the streets.
This is flooded in Tibet. And really flooded over here.
Sewage water in the. That's definitely not Gothenburg.
Exactly.
That's long. That's too
It could happen. That's why we put it over there, because there were all the animals that over there. And it can really flooding. So, but it has been actually long in Gothenburg for a couple of years.
There is 2 types of flooding. There is flooding according to the sea levels, that is sea rises and floods, and there is flooding because of rain issues. And we are only going to talk about the rain floodings.
Yeah. So I want you to give kind of a, I'll say this idea in your mind of like how much exactly rain and how much does it rain in Gothenburg. So.
Too much. We all do that.
You know the sensation of feeling the water. It's really nice. We're going to need a couple of different numbers about this. The annual precipitation in Gothenburg is defined as exactly as this. Like this.
So the rain is the rain, the sleet, the snow, and if you sum it all up, it comes to 758 millimeters per year. So almost 1 meter of rain every year.
So then we have the non-permeable area in Gothenburg. We're going to explain where we're showing this after these 10 numbers, and Linnea is going to tell you.
So 30% of the area in Gothenburg is not permeable. That's about 6,000 acres and 20,000 square meters.
So what is not permeable? I mean, maybe somebody in your doesn't know what's permeable. We have grass that is porosity is higher, so it's more permeable. Anyway, it infiltrates water. And concrete is not permeable, so it is runoff. That is why we
If the water falls here, it will flow on the surface. If the water rains here, it will filter into the ground.
Nice. So this is nice Gothenburg, not raining. And 30% of Gothenburg is not permeable. The other green areas, of course, the water is running up. So we're focused on that 30%. That is how much we wanted to show you about the area. And now with that,
We can calculate how much rain falls on the non-permeable area. And that is the water, like will end up in the pipe system. And if it falls on grass, it will infiltrate and not cause flooding. So this is the problematic volume. If we take the rain times the area.
And then you got a huge number.
45 million cubic meters of water are flowing on our coast each year. So how much is that? That's a huge number, even for us as individuals. So we have to convert it to something more comprehensive.
Exactly. So, you know this place.
You've been here, how many people have been to the Valhalla swimming pool? Quite a few. It's a normal 50 meters swimming pool, Olympic size, and it's 2,000 cubic meters of water in there. So how many Valhalla pools equals the same volume as the rainwater? It's some calculations and this is number 25,000 Valhalla pools that makes them. It's too that much. I don't understand it. We need to find something bigger to understand.
Exactly. So we have a model place that is actually really nice. And we calculate the volume. Model place.
Scandinavium. It has 130,000 cubic meters. So if you fill the whole Scandinavium with water, how many Scandinavian cubic? Any guesses?
It's like the street is maybe more understandable. We're still really so loud. I don't count it.
It's 353 Scandinavians full of water. So you see, we have a huge problem here. All of that water has to go down the drains, and no wonder it's flooding sometimes.
So, again, we have the pleasure to introduce to you Mr. Thomas Lab and Chalmers with showing our names and a huge name.
Bioretention planter for pollutant removal and stormwater control in Gothenburg City. So we're talking a lot about the flooding, and that's the stormwater control. So what about the pollutants? As soon as this is why we talk about the non-permeable areas. Because as soon as the rainwater touches the non-permeable area, that is the roads, the buildings, as soon as it touches, it gets contaminated. It's full of pollutions from the cars, from lights, from human activities. So rainwater is not as clean as it can be.
Yes. So, we're given a words of bioretention planter. We're going to explain to you. This is just a planter. No bio, no biological anything. This is just normal planter. Everybody knows the planter. This is the planter. And how we convert this planter as a bioretention planter. So we need to focus on the control of the water. We're working with the biological treatment, converting the bioretention one. And of course, there is a lot that is aesthetic landscaping to make it beautiful as this one. So, how do we control the water? Is we're going to collect it, absorb it, or redirection it, the water. And we're going to biologically treat the toxic metals and organic contaminants. I think we say that for you. There's a lot of toxic metals and organic contaminants, but for this species, we just focus on a couple of those toxic metals. No, just a few contaminants because they will be like a huge report. So for the moment, we're going to keep it like this, and then we're going to do it. And then the urban aesthetic and the visual amenity about the aesthetic and landscaping. So the combination of all of this makes a bioretention planter.
So how does the bioretention planter do? You take the planter and you put it on the ground. You can have different sizes, shapes, different plants. There's a lot of trees in it. But basically, it's green areas in the city, but with this important thing, the water can flow in.
So we have various designs, we have different colors, we have different plants.
And this is just how it looks when it's raining. When it's kind of finished. And this is what it is after the rain. So it's not that good. It looks really nice. See, this is how it looks. So we have we're going to explain to you exactly all kind of the structure just to make it visual. Really, that you have to make the explanation and how all the mechanisms works. So this is now we're getting a little bit inside that. This we're going to explain to you how did we came up with the bioenergy plan for the development city. So our method of research, this is a simple mathematical equation. We sum up two things and we came up with the fourth one. What did we sum up? We sum up that with the equal review. Yeah.
We studied design manuals of bioretention plans, mostly American.
And to make it really important, we told our stakeholders.
We're very pleased to see that some of them are good today.
Thank you very much. So we make the sum of these three things. We're going to explain you in class of each one of those. So again, we have the planter. Of all the books and all the readings and all the articles that we did in that time, we get with kind of four important dimensions. There was the cost of the bioretention planters. We focus on the phytoremediation, that is the use of plants to remediate the water and soil. Then we did maintenance of the bioplanters, and also the concerns about the community. But those kind of time restrictions, we just focus on the phytoremediation, because this is the kind of important part, the treatment of the pipeline.
So phytoremediation is another word, as Andrea said, for plants to treat water and soil. So we have the contaminants in the soil, and the roots suck up the metals and accumulate it in the tree. Or some other plants, they use enzymes in the root system to degrade the organic contaminants. So plants are actually really helpful when treating.
So another important point of our literature review, just to make in mind, because we want to combine all of this at the end, the choice of the type of the bioplanter. We're going to motivate this after, but this is the two of those bioplanters that you can get after studying all the minds of the literature. The flow-through bioplanter is the one that actually takes the water, not integrates in the soil, and then so that's directed or located in all the places. And the equation one is when we take that water and of course, integrate it in the soil. These are the two important bioretention planters types. There are different ones, but these are the main important. And we came up with the second part of the.
This is when we studied the design manuals and to come up with the size of the bioretention plant. What would be needed here in and for that you need to select the different type layers on the glass. We'll go more into detail.
We also need this equation, so take notes of it. Maybe this to get it. So that is just the equivalent search step. Just don't memorize that. Just we show you actually what you need about it. Another table equation. We try to not to put it so technical because we're not going to make really technical calculations over here, but another equation. It's just volume. So we just put kind of a really nice figure over here. And the surface area, more equations, but this is the surface area. This is now we're adding a really important one.
So, in order to actually implement a bioretention plan in Gothenburg, you don't only need the design manuals and the perfect engineering design, you also need the people in the city to be involved and to do it. So that's why we went to different stakeholders to ask for their improvement. We asked them how their organization would benefit from this idea and how they would like to improve it. So we went to Linnea, which has the treatment plant in Gothenburg. Kretslopp och vatten, which takes care of the pipe system. We spoke to trafikkontoret, as this often is placed near the roads, and roads are a big part of the problem for the contamination. and pumping nature. But this will take
And of course, stakeholders, teachers, and researchers in some universities. So, I think for the moment is we have a break. Next slide. Challenge Lab is has the pleasure to introduce to you a very important thing. So we're going to make it important. So this is the bioretention plan for Lundberg City. We're going to explain to you some kind of individual outcomes because we showed a lot of results. It would be a lot of results to show. So we came with outcomes and we try to explain to you the way you kind of make the puzzles to just complete the puzzle that is connected to the puzzle. So important with the bioretention planter, the first outcome was, I don't know if you remember what I told you, the flow through an infiltration planter. Why this is important? Because for Lundberg, we need to focus on the flow through planters, depending on the places that we're going to do it. But we have a really huge consideration when we're talking about soil. I don't know if most of us
probably heard about that. It's mostly clay and rock, and that is not very good infiltration.
Exactly.
So that's why we chose the flow.
So with this one, we can redirect the actual location in other location. Okay. Then another outcome was the drainage area. Why is so important? Because we need to know from works and for how many square meters we're going to take the water. The design manuals and they were like actually highlighting all the time that the drainage area hasn't been more than 200 square meters. But that is actually not that big. We actually kind of measure places in Lundberg, like this is part in front of Valhalla. And then we say like if the manual says that the maximum is 200 square meters, so we say we use 200 square meters. So how to show the screen by a planter in the city, how to show the biggest one that the city could have. Of course, it's better to have the smaller ones for all the places, but this would be kind of a huge, really big one for the city.
This is not the area of the planter, it's the area of the catchment. That's the area where the water is close. So for Gothenburg, then, how would the bioretention planter be structured? When we spoke to the stakeholders, they told us that a maximum depth of 1.5 meters could be used. So that was the limit we have to work with, 1.5 meters. And we have to fit 3-4 different layers in there. But for the bottom layer, which is gravel, we have 37 centimeters of gravel. And that is both to protect the piping that flows out of the planter, and also to store water. Then we have 100 centimeters of bioretention soil. That's where the magic happens. That's where the water is filtered, and the root system takes up the contaminants. So it's important for the big soil layer. On the top of the soil, we have a protection layer of mulch. It's just 5 centimeters, and it decreases the weed and it protects the surface. And then on top, we have some concrete boards of just 15 centimeters, but in case there's a really heavy rain and it doesn't have time to infiltrate, we can store it like in a small conduit area. So this adds up to 1.5 meters. That was the
recommendation. So after the selection of the layers, we came out with the sizing. I don't know if you remember all the equations, the amazing ones. So actually, that was our research. We made all the calculations and we're going to show you just how the size will be for Gothenburg City. So after the calculation of the
of the depth that was the maximum of 1.1 meter, we calculate all of this to think the surface area that there will be the surface of the construction. That will be the important one. If you don't have that one, everything will be like really difficult. So we calculate all of this, down the numerical method, but really difficult. So we came out with the important one that is 14.2 square meters. That is the area of construction for this extreme image area by the plan. But even thanks for the magic of visual arena, we have the area over here. So the area will be covered by the plan.
This
So-
is 14 square meters. But we're not standing next to it.
And of course, it's not going to be a green square. Really nice compass. So thanks to this area, to let us do this. This is the area, the bargain. So,
For the plants, we talked about field irrigation. The plants are, not all plants are suitable for it. They are very different in the amount of metals they can take up or the organics they can remediate. So some of the really good plants that are also suitable for Gothenburg will be here. One of them is the willow. And here you see the amounts of metal they can take up. So for copper, the willow takes up 8 milligrams of copper for every kilo of the tree. So for 1 kilo of tree, there's 8 milligrams. And that's the least price of 8 milligrams. The poplar tree also is very good for metal treatment. Then we have the winter dye, which is a tall grass, and that is very good to remediate the organic contaminants that we make. And together with this beautiful flower, alfalfa, they can remediate 70% organic. But the winter dye is a tall grass, and the stakeholders told us it's really important to make the bioretention countries look nice and fit in the local context in the city. So to place a lot of a field of high grass might not be so suitable. We look for our plants with more colors and they would look nice in the city. And yellow sweet purple also is good for remediation of them. And what is next? The sunflower. So these little pretty flowers actually also work really well to take up the meadows. For the copper, this one is actually better than the tree. Zinc, not as well. This one is also better. So the space was also something that the stakeholders were concerned about. Maybe we don't have the space to place trees everywhere. There's the sunflowers. Green and small.
So how, I mean, now that you know almost everything about how we can Lundberg, maybe we don't have enough, pictures, maybe not enough information, so we want to show you a video. It's already built and installed by a company in the US. But yes, so we hope that the video starts. Yeah. Half an hour ago was working with yeah, a quick break. So it's raining in Gothenburg, really nice raining. So all the water is going to come in the
with water getting inside the bioretention planter with all the garbage that the city has in town. So when it's getting inside, we have that is the mulch layer that is going to take over the garbage, and then all the water will come to the soil.
That is the written soil, and here's the roots, making the magic, taking out the contaminants with the feature remediation processes. These are just stored in the soil, slowly infiltrate, and this soil and the gravel layer.
And then we will take this water related to the river and we will store it. It will be nice because the water will be useful. So save it for another activities, take the place of the water, maybe also for So what happened with the when it's raining too much, when the precipitation is really high, the backwater just bypass the water. That is why they make this kind of scale of bioplanters. Maybe kind of sequence to try to catch all much water that we get. So this is how it works. If you want to see it again, this is the media. So we have an example of real example of how much bioretention planters we use for public purposes.
So this is a really picture. This is the Pusterbildsplatsen. This is the källare where it's fiskestugan. The means that it's much better. This is the parking lot. And it has 104 parking spaces there. So, and it has an area of 1,400 square meters. So, to put bioretention planters here, each, they are a size of 14 square meters. So, in order to take all the water from that area, and then we are counting around 50 millimeters of rain in 24 hours. That's a big rain. Should happen more than once every 10 years. But to collect all that water, it will need approximately 10 bioretention planters. And that might sound a lot, but look at the area. It's actually quite small compared to the parking lot. It would be the same as if you took away 7 or 8 of the parking places out of this 104. It would be enough. And also, look at the green area here. We have a lot of green area. It's already in the city. That could be.
So now that you have now we explained kind of a lot of results and outcomes of how the retention wonder, we want to show you kind of a highlight of how much a cubic meter of stormwater costs inside of our retention wonder. Why do we want to show kind of a cost? Because the costs, of course, are really important. We want to build it. We need to know how much we need to build. And also to tell that this is not only for the city, if somebody wants to build it, it will be, I mean, if the regulations actually allow it, it is good. So we made a really nice highlight. It was the cost for the water. How much it costs about a retention planter, 14 square meters, is the average of 80,000 Swedish crowns. This is the average. Could be more, could be less, depending on the area of the bioplanter. But this is the average, so we'll put the average. It's nice average. How much it costs maintenance? We know that according to the manuals and maybe what you have in the about 4,000 Swedish crowns per year. It's not that much expensive. It's just to take away the trash and to change maybe the soil and to change the mulch. This should be really nice. We calculate this cost per 10 years of lifetime of the bioplanter. It's also an average. It could be less depending on the places. It could be more. But we calculate for 10 years. So we made the with the 100,000, 130,000 discounts. That is the total we can use. So we have our bioretention planter for Gothenburg. It's 9.5 meters, the cubic meters per day. That is actually a lot of water. I mean, you will need a lot of water to fulfill that. But maybe just in case, something like that. So we have 34,200 cubic meters for 10 years for the bioplanter. And after all that we made the calculation, we know that Because we can have a bioretention plant for 10 years, only paying like 3.5 Swiss francs per cubic meter, or like 4 francs. So, depending, of course, if you only pay the 8,000 Swiss francs for 10 years, so if you have actually one in your place, it could be suitable for the place. This is the highlighter we want to present to you. It was another one, but we didn't have the time over here, so you can check what we work. Really important.
Do you remember anything from the presentation before us? Your face is not, you must have texts. Remember they talking about we set up criteria in the challenge lab. We looked at the 4 dimensions from the compass: the nature, economy, society, and well-being. They're all important parts of the sustainable society, sustainable future. So we made this criteria in challenge lab, and therefore we want to evaluate our bioretention method to see if it actually is sustainable, the comparative criteria. And the nature criteria was about not increasing substances in the ecosphere.
We have the same mistake that all of them. So if there's some substances from the
And this was where we started. We wanted to take out the contaminants, not only from the water, but also from the soil. There are many green solutions for water treatment, but most of them think about the water, and they don't think about the toxic substances accumulating in the soil. And that's what we take.
So we also think about the economy, that it's not only about how much it costs about the Lundberg. It's also investing in the societal infrastructure. It is not, if the city doesn't use the bioretention clusters, we know that citizens, with the regulation, of course, as I said before, it's a sort of each house over here. It could also be located or near to the buildings or to the environment. Now that you know that you can actually take some water after a bioretention cluster, you can use that water after. Of course, it's not drinkable, but you can use it after that.
Also for the society, one thing we found when we were talking to the stakeholders was they all liked the idea. It's fantastic with more green areas in the city, but maybe it's not our thing to implement them. I mean, the flooding problem affects everyone, but the responsibility is shared. And this could actually be a great opportunity for people to cooperate and to build trust within their societal institutions. But the great thing about it is that you can do it on a big scale with the municipality, with the collaboration, but you can also do it on a smaller, more individual level. If you're a household owner, you can put it on there. If you have a road where you know it's a lot of toxic substances, you can put it beside the road. So it works in both.
Yeah, what the well-being criteria is, we pass it to the criteria, and every little thing that helps the human aesthetic or the community contribution, you know, it makes you feel good, it makes you feel it improves your well-being. So after the whole examination, we analyzed the bioretention cluster, and of course this is just kind of a glimpse of what we came up with the bioretention cluster through the analysis of the challenge lab. Now, this can be the end of the presentation. We want to show more things, but we came up with some conclusions about it. That is something happening here. I don't know. Yeah, we don't have conclusions. there is
No.
yes.
So for the conclusion, it's gonna be a task now for you without having anything to say, just listen, take it over.
It was really nice to meet this club. Of course, the conclusion, the first one is, the bioretention planter after the challenge-like criteria is suitable, that is the word. So we know that not only improve about the nature, not only improve about economy, but also improve the society well-being. Is that we know that one of that conclusion makes us. The conclusion is that why Gothenburg doesn't have bioretention planters, so why Gothenburg didn't maybe work with other green infrastructure before. So we came up with this first conclusion about that under the bioretention planter, it would really useful for the city. You actually have the images. No, the second conclusion.
Well, so the thing we wanted to study was to see is bioretention planters suitable for Gothenburg. And what we came up with is, you saw the calculation, it can treat the volume, 14 square meters of bioretention planters for 200 square meters. And as Andre said, it's good for the different dimensions, society, well-being, nature, and economy. And we want to stress that this is an integrated solution, that you should not only think about the water retention or the cost, that you should also see the value of the aesthetical pleasing part of it. That even if it would be digging up new parks and putting them in place, but even if it wouldn't be, you would still need products for when you develop new area, you plan to put products. Why not make them bioretention products? And you don't have to worry about this. So making an integrated solution and use the nature.
Yes. We have some recommendations that we can use. So, of course, after the bioretention planter doesn't. I mean, the thing is not to treat all the water, all the some part of water. For that, one of the recommendations is to convert in one of the things. Let's do some quick treatments before and after treatments. The pre-treatments is near to the properties, and then pass it through the bioretention planters, so that we know that the water will be not that much contaminated. And after, of course, use that water maybe some ponds or streams. In the case of Gothenburg, the aim was to take away that water from the wastewater treatment plant. So that now that we studied this flow-through bioretention planter, we knew that that water maybe not that much will not go to the treatment plant, and we were going to help maybe not that much the.
At least a little bit. As there is a saying in English, a small acorn makes a big tree.
So the last one is what don't forget about the soil. So we're trying to clean all the water that we put, all the water that is in our hands. Even taking away that water from the system. Most of the places have to go about industrial facilities, so maybe other things that contaminate the soil. It could treat the water, but the soil is contaminated. So this, of course, the project was to understand how actually treat with water and make kind of soil. But if you want to implement these solutions, we want to remember, don't forget about the soil. So these are our missing, maybe not technical recommendations and conclusions after this presentation. So thank you very much. I'm very sorry for the
Okay, thank you very much. And now we welcome Johan and Amandine that are going to do the opposition. And after they're done, we welcome everybody to give their own questions.
Okay, so first of all, thank you for this very nice presentation. And I kind of felt from the beginning that I really hope for it. It was nice. And actually, when you showed the picture of Lucian and the parking lot, I thought Eric was starting to shake because he was planning putting solar panels there. But thank you very much for this clear presentation and the motivation of it. And as a really got to burnout for quite some time, I've experienced some floodings, and I'm happy that I live on Johanna Bay. So yeah, me and Amandine, we have now watched your presentation, and we've been also been reading your reports, and we have some questions.
Maybe to start with, you decided to focus only on free metals and pH trees. Could you tell us a bit more about what criteria and how you make those?
Well, I mean, it was most a matter of time of the report because the world, I mean, there are a lot of metals in the small water after the pressure ground. So if you took all the metals, I mean, the biggest one that actually are in the stormwater, I think you put it from Europe. Then you on the research of the plants, it would be a lot of plants. So then the pieces would be only hydroregulation and plants and forget about the other things.
To specify well, which is these ones, to do grass out, and we took the most toxic and the most common ones that we can find in soil. And the same for the organics and the pH. There's actually a lot of research.
How toxic is sin?
On the purpose of this work, you gave a pretty interesting example on the parking lot of residents. How could that be scaled up, and on what kind of, is it mainly target on parking lots and areas near roads, or how do you see that it be implemented?
We made a calculation of after one of the talks with our stakeholders, they give us how much water was actually bypassing the ground. Not bypassing it, but we call it flooding without any treatment. So every year for almost 10 days, it's kind of 2 million cubic meters of water flowing, not getting the proper treatment. I'm going to answer the question. So when you get all that big numbers, then we calculate how much bioretention planters will be needed to try to help those community and maybe young growers. And then we can ask the proper authorities. As we made a calculation, and we needed almost only using bioretention planters, like 21,000 bioretention planters to do all that on treatment of water in the plant. So then we said to locate 20,000 bioretention planters in the whole city. We think it's not an insane idea. It would work, but that is why we recommend other kind of equipment and all a complete system with
I mean, if you look at Gothenburg having 30% of more covered area, and this other 70% is actually parks and nature. So if you would convert all of that to, even if you would convert just 3% of that to bioretention project, it could handle this. But to find new location for it in the already existing part, not to, but when developing new areas, you should definitely do that.
So you have this, because there are two parts here. First, the flooding control, and then also the water treatment. But regarding the metals, the toxic stuff that is come up in the plants, what happens with that on the long term? Or we don't get rid of the metals?
The toxic metals accumulate in the plants, and then you harvest your plants and probably incinerate the plants, and from out of the ashes you can reuse the or even store it safely. So you do need to take it out of the system. Or it just degraded, it degrades it to a less toxic form. So some components are toxic in one form, but if they're transformed into something else, it's harmful.
When looking at your methodology that you use to visualize the equation of three elements, about the first one, you quickly mentioned that the design manuals you're using are maybe in the US. We were wondering how is that, and also is it a form that in the US is probably different titles than here in the US?
The first reason is all our research was in English, so most of the text and all the information was in English. Then after kind of a deep seeking, even in other languages, there was kind of a quest to try to look at a regulation in other languages. There is not actually a proper regulation about the use of human sensors. Even, I mean, maybe it is, but not with bioretention language. Then we came up that the conclusion of reading all of that is like these kind of structures are not suitable to put in the big city because they have space. They say even if you want to put on the sidewalks and near to the roads in the really main city of capitals and in the countries, they don't have space to put the bioretention planners. So they focus on all the infrastructure techniques. Gothenburg is suitable to put it in bioretention planners, not only because of really the space, there's already 70% of green area that can be used for it. It's because in the future there will be more areas, so the green plan of Gothenburg is
Gothenburg has to be more dense and then more green cities. So this could actually be a way to do it. But for the manuals, I think the states, they've come quite a long way. They have already implemented it in several states and United States now. It's basically easier to find out. We haven't found information for it. But we did convert, we didn't just take the numbers, we did convert the rainfall research.
And regarding the design, how come that you do the wall on top in this 115 centimeters?
How the polymer? Well, the polymer was designed for most of the security reasons because of those 15 centimeters. Actually, not two reasons because when it's really over. It's like when there's a lot of water and the bioretention plant doesn't have the capacity, it needs to bypass. So if after all these 15 centimeters, if the water is still going, there's the water of the bioretention plant and it's still running out. And also because if you put it on the level of the sidewalk, you also need a little centimeters to kind of tell the people too much to pump it to the bioretention plant. Also, I mean, a couple of cities in Europe use some kind of fences, small ones. But there's
So that is still like include. So that is included in this 150.
Yeah, it needs to be included.
Yeah, okay.
And also about the design, when you were reading your theory, it was pretty clear you detailed very much what are the different parts of the calculation, what needs to be designed first, and then how you come up to your final results. And you only present one way of calculating that. Is there any alternative ways of designing?
No, from all the manuals we have found, they all calculate in the same way. And it's basically area times how people value, and that's, I only learned that.
And then maybe more details. On the bottom of the order, we know that with climate change, the amount rain or polar increase. Was that any other part of the calculation?
Yes, yes. In Gothenburg today, we have found that it's 45 millimeters of rain per 24 hours. That happens every time of year. But they expect the rainfall to increase 20 to 30% in November. So we calculated for 50 millimeters. So we have taken some climate change.
And what we also calculate the cost for a couple of years that are from 10 years. So we design the cost also for the calculation of the consumption.
And if one of the main objectives was to reduce the impacts of floodings in Gothenburg, if you have that purpose, you can of course find different solutions towards this, such as increasing the diameters of the pipes and other maybe expensive solutions. How did you choose this solution?
Just swimming in the pool.
We actually had a lot of different ideas. We were talking about creating ponds in the city, but in the end we came up with this problem that it would be toxic water. The contaminants will increase in the ponds, and that wouldn't be as good for nature or for well-being. So this was the way to both do the treatment and the
And you actually gave the estimated cost of the roof installation and maintenance. Do you have any idea in comparison how costly or cheap would be the other option?
No, the valorization number is considered kind of costly, as on the implementation over time is really cheap. When you have to give it maintenance to a point or improve or interactions, spend more money every month of the year. It was only 4,000 per year when we take it out. So that was one of the biggest considerations.
We found some figures about how much it costs currently to keep in the waste and treatment plant. But it's kind of similar with the bioretention.
Maybe to finish like this, the third part of the method was about stakeholders. Could you be a bit more specific on what were the roles of stakeholders in your design process? And at what time you actually gathered what kind of data?
Quite early in the process, we had the idea of a bioretention closure. We knew the function and kind of the structure, and we came there both to ask them about what they know about the problem, what they are currently doing about the problem, and then ask how does the solution fit into the organization. And they gave include, say, things, they told us technical things like we can't put them this close to the road, they can't be a little bit higher than this, but they also said things like they need to be aesthetic as pleasing, we want flowers, we want plants that increase the biodiversity, and we try to take that into account when we design the final
And I think if I remember in the report you mentioned that this, as with company, this is a very nice way for you to achieve your dimensions and go through water managing flooding. Have you got more nuanced digital stakeholders, or are they already into it and ready to
There may be another last pieces about that.
Yeah. So what is the next step now? Now we have made this. What is like?
We wanted to make the prototype a real prototype, like you can touch it, see how it works and everything. But yeah, maybe it wasn't just the restrictions of our time. It was actually it was about time. Yeah, we didn't have the time to start to make it, and maybe it is going to be in a human scale. It will be affordable for maybe a company, maybe for a city, or if the university is actually interested in making it. We also received some feedback for each of the and other organizations to say we can actually try to make it and see if it works. Now, we know that it won't work within this moment.
Perfect. Thank you very much for your question. And the public now can ask more questions if they have.
You were mentioning that 70% of the city area is actually green area. Did you ever look into what are the retention capacities that these green areas have and how they treat the water if it ends up in the common water sources?
We assume that the green areas of today can handle the rain that is already falling on them. But when speaking to the park nature, they told us that if you take too much water from the roads into the parks, it actually drowns the plants. The parks are not, they're not structured in such a way. And if the roots stand in water for too long, the trees and the plants can actually die. So it needs to be designed to be capable of taking more.
So the green areas have a smaller water retention.
They have a smaller retention than the bio-retention.
No, it's when I don't know if you remember all these equations that we showed you, but which are kind of like boring to calculate everything. When we calculate the runoff coefficient, the equation takes all these coefficients of different soils. We just assume, but we need to assume a lot of things because of the time we didn't make the PCC. It was a challenge to make the PCC in this kind of way. So we just considered that all the area that we consider total not permeable. Yeah, when you do it in real life, when you do it in the way, you need to check that we need to see which coded people, the type of soils, different coefficients, and then you calculate the general runoff coefficient, and then you do it again. Maybe that way, yeah. We know that not all the waters coming to the green areas are equally. So we made it just to make it actually in an extreme way also. So that area that we choose to the drainage area, all the not permeable waters that will give us that 14 square meters by diameter. So in theory, that was just extreme way to see it. In theory, it's smaller. But if you like it in that way, 14 is typical of what.
There is I can tip you. There is a retention plant with planters being built at Kviberg at the moment. Have you looked at it?
We haven't been there and studied. We've heard about it.
Yeah. I think there have 4 different versions or ecology and different plants suited for different, I think, times of the year as well.
That's another important aspect to take into account. But we haven't started.
Yes.
It's a nice presentation. It includes both the production of snow matter and also production of water, especially the production of water. But I was curious on the rate of absorption of that soil strata, especially in the rain, because the grass has a tendency to absorb the normal water for some millimeters each time. But for that strata, it's a flood coming at the time, it's a collective flood, and the rate of water discharge is a little bit more concentrated than the rain. So how is the rate of absorption of strata? Because still it's going to end up to the next storm line, which is going to still be flooding. So how is the rate of absorption of strata so that it will reduce the flood?
So again, if I understand, is how the different layers take the water. Is it,
I mean, the system, the 1.5 meter system is going to be built before the rain matters, before that population. How is the rate of leaking that water going to be coming at time? Because the rain has.
oh yeah, I mean, we took the bioretention layer of soil that is 1 meter something. It's a mix of different, there can be different minerals and sands and whatever. With that, I'm going to this one. With that, actually, we maybe not calculate. I mean, how much time before the water will come inside. But even when we assume that all the sand, I mean, all the system was going to contain that 9.5 cubic meters of water, if that is per day, yeah, 9.5 cubic meters per day. If it overpass that, if all the water just come out of the system. So we didn't make all that calculations for different layers of the soil because it was going to be one of the yeah, right. I mean, it was a nice adding to see how much different layer was going to take the water and time. Maybe if I understand that question.
I think the pollution control idea is good, and I was thinking maybe it's good to put this pollution control at the end of the start of pollution.
Oh, yeah.
The start of party, because still that's the same amount of water you're going to join the streams of the existing diameter system. It will still grow or be more efficient to get that water. So the flood control will be done also by this
No, we're not going to check all of the water as you said because this is just what's going to be the overview of just this structure of the utility. But as we recommend at the end, when you need a whole the whole system, maybe something before, maybe something after, but not essentially maybe something before does not control. We try to concentrate kind of the pollutants and the water. Then we take the water and we pass it through the bioretention plant. Then the water will be more clean in that way, and then we store it in the ponds, in a really nice ponds and ponds or something. In that way, it will be possible to have ponds, but it has to be in the whole system. Only the bioretention plant is not enough to control it.
Just 1 month ago, we finished the Chalmersplatsen, stone desert.
Yes.
And of course, when that was built, if this wasn't the plan in the beginning, I imagine it would cost very much more to introduce this in that stone desert instead of other whatever it is. So if you are there in the design phase, I think because the alternative cost is also there. You have to do something with the area. And if this area is nice and it's fulfills some other purposes like whatever. So that would be very interesting to look at the campus area now and see where can it be, because things will happen around Lundberg Södra now. Will be stone there as well. Or should we take the advantage of interest? So maybe you can, if you have time now, to write a proposal to make a small survey over the campus area where this could be introduced. Because the campus development group has a meeting next Wednesday. So send a little proposal. If you want to do some summer studies on someone to do some survey, what could happen in the campus area for a suggestion for future day. But this is a possibility before next Wednesday. it can go whichever way, but it has to end up in the Kempström group, and then it's next Wednesday.
I'm thinking about the possibility to introduce these bioretention plantings in a larger scale. What's the most challenges or what's the most important hindrance for introduction? Where do we need to start?
Still with the regulations, I would say. To where they can build there's not place for them. And where you have a nice size of furniture.
But the important one is the design that doesn't have to be more than 5% slope on soil. So we just can't put the right planters over there. You know, the planting for us is 9 skills. So we just can't do it. We need kind of 5% there. So it will be like down of the middle mountains of the planters. And that actually restricts a lot of locations to go with our planters. Even if we know that get flooding in some places, the background can't be diagonal. So that main challenge, that is one of the biggest challenges. If you start too close to the part of we'll start to really, I mean, we already have the maps and everything, just to kind of which place is the best. That's the first challenge. There's a lot of them.
Okay. Just a recommendation also, I think if you have some time more, calculate the economical value of zinc, copper, and nickel. I think it's a rather high value in the soil working so maybe the cost to show us will be nothing compared with the economical value. If you manage to recover this from the soil and from the plants, I think it's rather easy to do this calculation.
And if you look into the challenges that Chalmers buildings have, with enormous areas, surfaces of copper, you could do a good thing for Gruyab. They would love you. If you could reduce the amount of copper running into the switch. So introduces.
So copper roof and stone desert is top of the line.
We work with green and clean stormwater solutions.
Perfect. If there are no more questions, then we can come back at 14 past.
I've been. You can stop the broadcast.